Bismillahirrahmanirrahim. We have a sequence of i.i.d. positive random variables from x1 to xn. We also have positive constants, 𝜃1, 𝜃2, 𝜃3, and so on. They are in a non-ascending order. The goal is to prove that 1 over the sum of the thetas is a lower bound on the expectation of xn divided by summation I from 1 to n 𝜃ᵢXᵢ. Note that if all the thetas are equal, the right-hand side is equal to 1 over n theta. The left-hand side is 1 over theta, expectation xn over the sum I from 1 to n of xi. The expectation of the sum of the random variables divided by itself is equal to 1. By the linearity of the expectation, this is summation j from 1 to n, expectation xj over the sum. Because the random variables are i.i.d, all these expectations are equal. This sum is equal to n times the expectation of, say, xn divided by the sum. This expectation is 1 over n, so the left-hand side is also 1 over n theta. If the constants are equal, we do have equality. For the remaining part of the solution, we can assume that not all the thetas are equal to each other. Let's write the expectation as the expectation of xn divided by theta n xn plus summation I from 1 to n minus 1 𝜃ᵢXᵢ. Suppose that n is equal to 4. This expectation is expectation of x4 over 𝜃4 x4 plus 𝜃1 x1 plus 𝜃2 x2 plus 𝜃3 x3. If I permute the random variables x1, x2, and x3, what happens to the expectation? For instance, suppose that I have the expectation of x4 over 𝜃4 x4 plus 𝜃1 x2 plus 𝜃2 x1 plus 𝜃3 x3. I swapped x1 and x2. Because the random variables are i.i.d, this expectation is exactly equal to that expectation. We can permute the random variables from x1 to x3 in 3 factorial or 6 ways. We can produce 6 expectations. All of them are exactly equal. I can write the expectation of x4 divided by 𝜃4 x4 plus 𝜃1 x1 plus 𝜃2 x2 plus 𝜃3 x3 as 1 over 6. And then we have a copy of this expectation plus 5 other expectations that involve the 5 other arrangements of the random variables x1, x2, and x3 for a general n value defined by to be a permutation of the set of positive integers from 1 to n minus 1, exploiting the linearity of expectation. The expectation of interest can be written as expectation. We sum over pi the permutations. We have 1 over n minus 1 factorial, xn divided by theta n xn plus summation I from 1 to n minus 1 𝜃i x pi I. For instance, the permutation applied here is that we take 1, 2, 3. Pi of 1 is equal to 3. Pi of 2 is equal to 1. Pi of 3 is equal to 2. Consider function g of alpha that is equal to beta over gamma plus alpha. Beta and gamma are positive real numbers. The second derivative of this function with respect to alpha is equal to 2 beta gamma plus alpha to the power minus 3. The second derivative is positive. Function g is convex. If g is a convex function, then g applied to a convex combination of the alphas, those lambdas are non-negative and their sum is unity. G is upper bounded by the convex combination of g of alpha small k from 1 to big K. Inside the expectation here, we have a convex combination. The coefficients are all equal to 1 over n minus 1 factorial. There are n minus 1 factorial of them. Their sum is 1. We have a convex combination. In our case here, the parameters of function g are beta equal to xn, gamma equal to theta n xn, and what we have here is the argument of function g alpha. We leave the expectation as is. This sum is here. On the right-hand side, we apply function g to the convex combination. Beta of function g is xn, gamma is theta n xn. Now we have a convex combination of the arguments. That's 1 over n minus 1 factorial, summation over pi, the permutations, summation I from 1 to n minus 1, 𝜃i x pi I. Swap the order of summation. We have summation I from 1 to n minus 1, 𝜃i, summation over pi of x pi I. When we do the permutation, in position I, xj for every j from 1 to n minus 1 appears n minus 2 factorial times. If we go back to the special case, let's see 𝜃1. It's multiplied by x1 in this permutation and that one. It's multiplied by x2 here and there, then by x3. Theta2 is multiplied twice by x2 in this permutation and that one. It is multiplied by x3 here and there. And here it is multiplied by x1. We have n-1 factorial permutations. Each one of the n-1 random variables appears in a given position n-2 factorial times. n-2 factorial is the number of permutations applied to the other random variables. In the general case, theta1 is multiplied by x1 n-2 factorial times. It's multiplied by x2 n-2 factorial times, and so forth. The situation is exactly the same if we consider theta2 or theta3 or any theta all the way to theta n-1. Every theta is multiplied by n-2 factorial times the sum of the random variables from x1 to xn-1. This double sum here is n-2 factorial times the sum of the thetas times the sum of the x's. n-2 factorial divided by n-1 factorial, that's 1 over n-1. Multiply numerator and denominator by n-1. The expectation of interest is greater than or equal to the expectation of n-1 xn divided by n-1 theta n xn plus the sum of the thetas to theta n-1 times the sum of the x's to xn-1. Rewrite this sum as the sum over all n random variables minus xn. We write this expectation as the expectation of n-1 xn. Downstairs we have the sum of the thetas from I to n-1 times the sum of all x random variables. We still have this sum times xn. There is also this part here. Divide the numerator and denominator by the sum of the random variables. Recall that the thetas are positive constants. They are in a non-ascending order. Theta n is the minimum. We are now tackling the situation in which at least one of those thetas from theta1 to theta n-1 is strictly greater than theta n. So this part is strictly positive. Let's consider another function. H of alpha. Alpha is between 0 and 1. Alpha plays the role of xn, which is one of the positive random variables, divided by their sum. In the denominator, we have a positive constant, beta, minus another positive constant, say gamma. Then we have the same argument, alpha. This is the sum from theta1 to theta n-1. This is the same sum, and we are subtracting a positive quantity. So in this function, the parameter beta is strictly superior to gamma, and gamma is positive. The second derivative of function h is 2 beta gamma times beta minus gamma alpha to the power minus 3. The second derivative is positive. Our function here is also a convex function. We apply the same trick again. Note that if we replace xn by x1 or x2 or any of these random variables, the expectation remains the same because they are i.i.d. So I can rewrite the expectation as summation v from 1 to n, 1 over n, n-1 xv over the sum divided by the same denominator with xn replaced by xv. The function is convex. What we have inside the expectation can be lower bounded by function h itself applied to the convex combination of the x's. n-1 is just a constant. Then we have summation v from 1 to n, 1 over n xv over the sum of the x's divided by this constant minus that one. This part is replaced by the convex combination. Let's simplify. The sum over the sum, that's 1. So we have n-1 over n. Downstairs, we have the sum I from 1 to n-1 theta I minus the same sum. We subtract n-1 theta n. The sum of the random variables divided by itself, that's 1. We are left with 1 over n. Note that the random variables have disappeared. This is the expectation of a constant. That's the constant itself. Multiply the numerator and denominator by n. We get n-1 over n summation I from 1 to n-1 theta I minus summation I from 1 to n-1 theta I plus n-1 theta n. This part is n-1 summation I from 1 to n-1 theta I. Divide numerator and denominator by n-1. We get 1 over summation I from 1 to n-1 theta I plus theta n. And this is the reciprocal of the sum of the constants from theta1 to theta n. This was our target lower bound on the expectation of interest.